morning, everybody. First of all, thanks to my previous speakers for setting the stage. We will continue with sediment transport, and we will be looking at very extreme case. I would call it what Bruno Merz also called yesterday the HILP, the very high impact, low probability event. And I will make the argument that we need to look into the past to detect these events, and we have good chances, in particular in the Himalayas, to gain more knowledge about these events when we do geomorphological work. So, but first of all, why is sediment actually a problem? We have heard of it before. It's just a kind of repetition from that. First of all, on a very short term or short time scale, sediments like big boulders exert quite a peak impact load on any structure, like dams, like on bridge foundations, stuff like this, where you have a very high impact from individual boulders during floods. You have the alteration of channel geometry by deposition and erosion, which leads to different flood behavior in the upcoming years. You might have blockage and damage of drainage systems by sediments, as well as reservoir siltation, which lowers the lifetimes of reservoirs in the end. Turbine abrasion is a big problem. Turbines are extremely expensive in hydropower plants, but are easily abraded by just sand and suspended sediment. And of course, you have a long-term modification of flood behavior by sediment. These are all negative things. On the other hand, we need to recognize that sediment is part of the natural process and part of the natural erosion and denudation that goes on. And that must happen because the mountains still rise, and they keep rising. Like the Himalayas have maximum rates of up to 2 millimeters perhaps per year. And well, this material has to go somewhere. So erosion is part of it, and it needs to be managed, as Axel has also pointed out before. You have seen these pictures before. You will see that I will show a lot of pictures, but sediment is not only an issue in the Himalayas or alpine regions. We have seen the R flood, where a lot of sediment was mobilized and created big problems. We've also seen that picture before. It's one of my, would be bad to call it favorite, but it shows the impact of sediments on the hydropower project Vishnu Prayak. For those who will accompany us to our excursion, we will pass by that hydropower project. So remember those pictures and you will see how it looks today. It has been cleaned up, but in fact, what we see here in terms of the sediments, well, they have been excavated afterwards again. That was during the 2013 Indian floods that mainly impacted Uttarakhand. So what triggers those extreme sediment fluxes? There are different ways how they can actually be generated, and I would say, well, first of all, co-event landslides and erosion. So just distributed all over the landscape, where you have a relatively strong rainfall event or period of rainfall. If the soil has no capacity to hold the water anymore, and if shear stresses exceed the stability of the soils, well, you would have co-event landslides as well as massive erosion, and all of them together basically bring a lot of sediment into the rivers. We have seen that in the 2013 Indian floods, and similarly the Gorkha earthquake in 2015 generated more like 20,000 landslides, which of course also increased the sediment load of rivers. Of course, you might also have events of extreme sediment fluxes that are more connected just to a single input of sediment into the river system, as during massive landslides and massive debris flows, glacial lake outburst floods or landslide lake outburst floods. The Chamoli disaster is one of those. Again, we will see these once we're in the field. In 2023 also, Sumit Sen mentioned this one, the South Lonak Lake outburst. Mobilized, I think about 50 million cubic meters of water. But what we reckoned, it's even more sediment that has been mobilized all over the flow path of that outburst flood. At times, you also have the tapping of some individual sediment sources. Now this happens if you have some loose material lying around, and which often occurs if you have, for example, a landslide dam, which was infilled by sediments over time. And once the dam material, which is usually quite coarse, is eroded or incised, then suddenly you get a lot of sediment from the upstream former impounded volume. And that might have contributed to a flood that you also see on that image here, the Melamchi flood in Nepal, where such a mobilization of a former landslide dam caused such a sediment aggradation further downstream and concomitant problems. So as in landslides research, where you talk about triggers and predisposing factors, we could also ask, well, what are then actually those factors that prime landscapes to generate these extreme sediment transport events? And of course, it's those landscapes that have a high seismic activity, so where you have a lot of earthquakes. It might be those landscapes where you had a tremendous change in land use and land cover change. Think of parts in the Himalayas where terraces are still or have been a way to make or to create agricultural space. These terraces are being abandoned more and more, and if they collapse, this creates tremendous problems. There are other human activities related to construction, which lead to a lot of sediment input into rivers. So the Chopra report, for example, said that this sediment input and the flushing of sediment, for example, created some severe problems during the 2013 Indian floods. But then there are also other more longer term processes that we need to look at. That is permafrost decay and concomitant slope instabilities, glacial debuttressing, which means that when glaciers recede, you would have a change in the stress on the neighboring hill slopes, which could lead to a catastrophic failure of hill slopes. Overall, you might look at both permafrost decay and glacial debuttressing with the term periglacial adjustment. So everything that happens after or during deglaciation is something that we call a periglacial adjustment, so an adjustment to some new climate conditions. And finally, on even longer time scales, river incision might play a major role in undercutting hill slopes and then generating these kinds of events. One of the difficulties that we have nowadays is perhaps what the media ask, what people are asking. Well, can we expect that these kinds of events or processes will actually increase the frequency of such extreme sediment transport events in the future? And it's difficult to say, because these events tend to be so rare that it's difficult to do any statistics about increasing frequencies and so forth. So I advocate for an approach where we would rather look into the past and see whether we see a more frequent behavior of more frequent extreme sediment transport events than in the past. And what I would like to do in the next, or in the remaining part of this talk, is to showcase how this can actually be done. And what I want to offer you is just an insight into how do we as geomorphologists actually work in the field. Well, we talked yesterday already, and you have seen, okay, I've done mainly modeling stuff, but that's not true. I'm also doing a lot of field research, and that's what I want to present to you today. This research is, however, a few years old, so bear with me that this is not just the newest stuff that I'm presenting today. So where we are going to go, that's Pokhara. Pokhara is in Nepal, the second largest city. And this is not the city right here, it's the northern fringes of the city. What we see here is just, first of all, an overview of the landscape. Here's the Machapuchare. It's the fishtail mountain, kind of an iconic mountain because just of its extreme shape. There's Annapurna 3 here, Annapurna 4, I think Annapurna 4 is above 8,000 meters. And then there's, in between those, there's the so-called Sapche Cirque. It's a glacial cirque, which is or where these mountains assemble around. And in the end, you have a river that drains this cirque, and it's called the Seti River. So Seti means white, I think. It's because this river has very white color, so it speaks of it very high concentration in suspended load. And what you also see are those beautiful alluvial terraces. Okay, so these relatively flat-lying sediment accumulations here, which have been incised also by the present-day Seti River. But you see, apparently there was a lot of aggradation going on in the past. So, and what I want to show is that, in fact, not all of these sediments here, but a large part of those was actually accumulated just very recently in geological terms. So only 800 years ago, the Pokhara Formation, which you see here, was catastrophically emplaced. And it's not just this area. So it was a much more extensive area. Let's zoom out a little bit. So the picture that you have just seen is taken from that hillock here into that river. That's the Seti Gorge. Here's the Sabja Cirque up here again. And so the Pokhara Formation itself is much, much bigger. It extends over 70 kilometers down to approximately that point here, has a thickness of up to 100 meters. So we are talking about a total volume here of 4 to 5 cubic kilometers of material. Okay, so that's much, much more than all the landslides and stuff that we have been talking about so far. It's one of the largest landslides basically that's happened on Earth. So the biggest one is about 20 cubic kilometers happening in Iran a long, long time ago. Okay, so how do we work as geomorphologists when we want to learn about such an event? Well, it's like working like a detective. Okay, you try to assemble all the evidences and try to make a story out of it. And the first thing we might look at is just the geometry, just the topography. Well, that I like to work with topographic data, that's something that you know. Now, what can be seen here when we look at this large accumulative region here where Pokhara is also located is that unlike other basins, so topographic basins like the Kathmandu Basin or so, they are more bowl-shaped. This one is different. You know, you see convex contour lines. So it means what you have here resembles more like a big fan that is perched onto that landscape of the Lesser Himalayan here. So that already speaks for that, you probably had quite some rapid aggradation. This can also be seen when you look at the fringes of these accumulations, that there are some lakes. Lakes are not so common in the Himalayas. So usually when you see some, then you need to wonder, why are they actually there? And here it's the case that, well, apparently these valleys, these tributary valleys, have been dammed by these deposits that were brought down years back. It can also be seen that in some valleys, you can trace the sediments into the tributaries. So for example here, that's a cross-section of a stream which is even further south. It's here, it's this one here, where you can trace back the sediments up to 7 kilometers upstream into that tributary valley. And you can even see that the terrace elevations do actually decrease if you go against the flow direction. Oh, 5 minutes, good. That's how these deposits look like. So that's the other thing that we look at. The sediments, that's me for scale, and Anne Bernhard. You see debris flow deposits recognized by their upward fining sequences, and then also large and extensive beds of fluvially transported material, but without any cross beddings or so what you would expect, but rather it was more like a fallout from suspension, but of very coarse material. You can also see stuff like this. These are lode structures or flame structures that evolve when you have a lot of material being deposited on soft sediments. It's also something that you see when earthquakes happen and you have soft sediment deformation. But here it's just the impact from the overlying debris flow that reworked to some degree the underlying soft deposits. The next question then, of course, is let's skip that one. What's the age of these deposits? Well, here we are lucky that you can see there were individual leaves still buried in areas where you would have deposits of the waning flood, so in the tributaries mainly. And at some layers you would find a lot of organic material, also large tree trunks or branches that you would find in the deposits. Here, this is a soil pocket that has been incorporated into a debris flow, and then the debris flow frees basically, and the soil pocket got preserved, or you have some muddy layers in between. The good thing is you can look at those with radiocarbon dating. This is another example of how to be able to constrain the age of these deposits. That's a boulder that lies on top of the Pokhara Formation. It has a circummeter or perimeter of more than 30 meters. You can see that sampling the top of that boulder was a bit scary, so we didn't do it. There was a voluntary guy who then just went up here, climbed the rest, and then chipped off some rock from the top, which we then were able to date with cosmogenic nuclide dating. Overall, we get a picture from all the 14C ages, as well as the age of Bim Kali. So it's because the god Bim threw that stone in telltale stories. But you can see a quite consistent picture of the ages of these of the formation, which ranges between, well, 1,000 and 1,500 years before present, but with major peaks being located about 3 major earthquakes that happened in the region. And one very prominent one was the 1255 earthquake that where like half of the population in Kathmandu got killed. And so it's very likely that this event was also happening at that time. So when you do field work like this, well, what are the challenges? Here, when you work in the Himalayas, you have a problem of accessibility. It's difficult to get to those regions. Pokhara was easy. Of course, when we want to answer questions about these extreme events, then we have a problem here, because in a quickly eroding landscape, you usually don't preserve these sediments for a long while. And preservation, well, that happens if you have very large events, like we had here. So there's a bias towards the large events. The sedimentary architecture, as we had it here, was pretty clear, I would say, even though previous analysis and studies said, well, these must be Pleistocene glacial outwash plains. Okay, so even that was not really clear until then. You can confuse a lot of these, let's say, landslides and stuff like this with glacial landforms. People that are glaciologists basically see mainly moraines in these, whereas people that work on landslides see landslides. That's how we happen to work. And one of the major issues is geochronology. So in fact, we have problems in dating these landforms, since usually organic carbon is not preserved in these deposits. We're very lucky, but usually you won't find anything. Other techniques like optically stimulated luminescence could be a solution, but prove very challenging, as a recent study by us showed, also for the Pokhara Formation. So our hypothesis was, well, we would have an increasing bleaching the further we go away from the source, but in the end, the data didn't show anything. So the model and the data, not really consistent. Last thing that I want to mention is, and also something that Sumit Sen also mentioned, we need to think of relaxation times. So relaxation means, in system theory, the time until after perturbation, a system goes back to an equilibrium or to some steady state. And this is something that we can observe quite nicely in Pokhara. So for example, we didn't see those tree stumps in some previous years when we worked, and after some while the river incised even more and exposing those ancient tree stumps. There is an abandoned terrace here that can be seen in corona imagery, so from 1960s, 1970s, where there was still water. Now the river has incised. We can reckon with about 16 centimeters per year of incision over that time period, between 1967 and 2016. And that also expresses itself in problems with bridge foundations and so forth. So the longevity of infrastructure in that place is definitely a problem, simply because these rivers are so dynamic and quickly incising that, yeah, none of them will stand for long. I don't have any conclusions because I think I said most. So here's just a nice picture, and I'm now looking forward also to your questions.